All right, so we started section 2.4, the chain rule last time, and the chain rule looks like this. The derivative of a composite function, which means a function that's embedded inside of another one, is the derivative of the outside with, the inside rewritten exactly like it is. And then we multiply that by the derivative of the inside function. And we're on number 4, which looks like this. So number 4 is not a terribly complicated looking one, especially if you want to compare it back to problem number 3, right? Yeah, 3 is very complicated looking. This one's not. And in fact, you might even look at this and say, I don't even see an inside function. And one of the ways that we look for inside functions is we kind of question, like, where are the parentheses? And there aren't any parentheses here. But if you were to put this in your calculator would force some parentheses to be a part of it. At least most of your calculators would. It would put parentheses around the pi and the x. Okay, so that is our inside function because that's the part that would be forced to be inside of something else, and namely inside the sine function. So when we're taking the derivative on this, we first focus on the sine part on the outside. What's the derivative of a sine function? It is cosine. Now, it means nothing to write cosine. Hopefully you remember that from trig. If you just write cosine, it's like writing down square root. What does square root mean? Well, it matters about what's underneath it, right? Same thing for cosine and sine. They don't have any meaning apart from an angle measure that's inside of them. So that cosine has to have the angle measure, and it's the same angle measure, pi x, that it originally had. So the inside stays the same. This piece, whoops, that's not a good color. Let's try a different one. This piece will match this piece when I take the derivative of the outside. And then that blue piece, I need its derivative. So pi x, pi is a number multiplied by x. Okay, so what is a number multiplied by x when I take its derivative? It's just the number. So this is just times pi. And on a gateway, that's exactly where you would stop. But for what we're working with now, we'll clean up what we can. We'll move the pi to the front. This is cosine pi x, like that. If you don't put the parentheses around the pi x, it's okay. They're understood to be there, whether you write them this way or not, because of the multiplication feature with them. Okay, number 5 has another trig piece to it. Is this one okay on 4? Okay, so number 5, again, it doesn't look like there's an inside function, but then you might say, okay, but just a minute ago, Dr. Hands, you put some parentheses around angles, the things that come after it. So there's my inside function, and you're right. That is an inside function. But there's another inside function here as well. Do you see that power 2? Yeah. So that power 2, again, if you'll remember from a trig course, that power 2, where it's located, means that the cosine function is squared. And we have this notation to try to not confuse the issue of what's being squared. But what it really means is that we have the 5 at the front, and then it's the cosine of my 3t and all of that is being squared. Sorry, I left my 3t in the red parentheses to try to isolate and make sure you're seeing that it's not shifting anywhere. But part of why we have this sort of, where we put the 2 by the cosine in trig is to simplify our need for lots of parentheses, right? In order to really write this out fully in a way that we can comprehend all the pieces and what's being squared, we get to have a lot of parentheses if we don't have this feature where we can put the 2 right beside the cosine. However, rewriting it the way that we have makes it a lot easier to identify what's inside and what's outside, because I see 2 sets of parentheses now, right? So not only is there going to be an inside function, but there's going to be 2 inside functions. Okay? So the process works the same way. It's just one step beyond what we've already done. So let's start first with what's inside. And I'm talking about everything inside the squared. So everything in blue is my first inside function. Be aware inside of WebAssign, They will pay very particular attention to your variables. So if the question has a t in it, like this one does, your variable needs to be t. If you put x, it's going to tell you it's wrong. So for the purposes of the gateway, they'll all be x's, so you don't have to worry about any of that kind of thing. And I tend to just use x's on my tests because I don't want your t's looking like plus signs and trying to figure it out. So, but just pay careful attention in WebAssign. They will be particular. Okay, so the blue part right there, I've sort of blotted it out in some sense because I don't need to focus on it right now. So the 2 on the outside and the 5 at the front are going to be involved in the outside part of the derivative because they are outside the blue highlighted piece. So I've got this sort of something raised to a power of 2. That's a power rule. The 2 will come down and it will be multiplied by the number that gets carried along for the ride, the 5 at the beginning. So I usually will go ahead and multiply those because it's pretty straightforward to do so. If you don't want to and you just want to write down 5 times 2, feel free to do that. That's fine. The part that's in blue, right, the blue part here gets rewritten. I'll do it in a second. And then I decrease the power to 1. So it's 5 blue squared. Well, that's 10 blue to the 1. And that's what it is. The blue part gets rewritten. So that's the cosine of my 3t. Now I need to take the derivative of the part in blue. But the part in blue is much like this problem over here. It has another inside function. Okay, so the outside part on this one is the cosine part, and the inside part's the 3t. So we're working our way outside in when we're working with derivatives. The outside cosine is what we're on now. What's the derivative of cosine? Negative sign. And remember, I can't just write negative sign and close this off. This has no meaning. Means nothing. It's like writing a random square root in the middle of your paper. Does not mean anything. It needs the angle next to it to have meaning. The angle next to it's 3t. So now I've taken the derivative of the outside squared part. I've taken the derivative of the cosine part. Now I'm working my way in. I need the derivative of the 3t part. What's the derivative of 3t? 3. This is the full derivative of this function, and I guarantee on the gateway you will have things that will have more than one inside function show up in a couple of places. Right? Can you identify that you have functions embedded and that there's more than one of them? Right? Like that's part of identification of what we need to be able to do. Now, we need to clean this up too because this is kind of a mess, at least for the purposes of generally, right? Not for the gateway. The gateway, you'd leave it just like that. But with a cleaning up step, this 10 here at the beginning, this 3 here at the end is going to make 30, and there's a negative, so I've got negative 30. And then I have the cosine of 3t, with or without the parentheses, and the sine of 3t. Is that all right? All right, let's take a look at number 6. Okay, number 6 has pieces that start to look even more like what you're going to see on your gateway. Some of the pieces may be very straightforward. I can just do that with one of those simple, really quick rules from 2.2. Some of the pieces are going to look like product rules. Some of the pieces are going to look like chain rules, and they can all be present in the same problem, right? You have to be able to push them all together is the idea. So when we're looking at this one on number 6, we see the 3x at the beginning. That one's easy to do. What's the derivative of 3x? 3. No problem. But the next part is messier. In fact, it kind of looks like this one. It's got a squared, but the squared is in a different location, isn't it? The 2 here is after cosine, and the 2 here is after the parentheses with the pi x in it. Is it different? Does it matter if the 2's there or if the 2 had been written right here? Do you know? So the answer is it does matter. The 2 where it's written right now means that that power of 2 applies to the pi and the x. It doesn't apply to the cosine. If it applied to the cosine, it would actually be written like this. Do you see the difference? So it's not really meant to trip you up, but it's the notation that's commonly accepted and that we have to work within, right? It's kind of like the English language. I think everyone in here is a native English speaker. Is that true? Okay. So I have children in my house who are non-native English speakers, and they don't like English sometimes. English is hard. Do you guys know how hard English is? It is so hard. But I don't get to change the rules of English because my non-native English-speaking daughter doesn't like it, do I? She has to learn to work within the system that she's in right now, and that's how we are doing with this stuff too. We don't have to like the fact that the notation looks really confusing, but we have to work within it because it's the commonly accepted notation in the mathematical community, okay? Just like English is in our English-speaking communities. So when we're looking at this 2 right here is on the pi and the x, not on the cosine. So I'm going to highlight this piece of it as being my inside function because all of that is now embedded inside of cosine. So I have minus the 5. Okay, so what's the derivative of cosine? Negative sign. So I'm going to actually put the negative here by changing my negative 5 to a positive 5 and write this as sine. If that bothers you, just take a couple steps to do it. And then the blue part gets rewritten exactly like it was before. Now you had a couple of options here. If you want, you can write down that the pi x squared is actually pi squared x squared, and you can do it from that perspective. Or you can leave it written as pi x squared and recognize you have another inside function. I'm going to do it from the inside function perspective just so that you can see it, and then I'll do it from the other one so you can see the difference, okay? And then you can pick which one makes more sense to you, and it doesn't really matter. If we do it from an inside function perspective, the 2 on the outside is now a power rule, and it comes down. The part that's inside, the parentheses gets rewritten, and my new power is 1. That's dealing with the 2 like it's a power rule, right? With a chain inside, the inside pi x, the outside power 2. But then what's the derivative of pi x? It's just pi. Okay, so this is one way of dealing with it. We'll clean it up in just a second. Let's deal with it another way. 3 plus 5 sine pi x, we'll do pi squared x squared. So if we think about distributing this, because it's multiplication, I can distribute. I can actually take the derivative of pi squared x squared. Well, pi squared is a number, right? I know it's squared, but it's just a number. It just comes along for the ride. What's the derivative of x squared? 2x. And it would look like this. Now compare that. Pi squared 2x right here. 2 times pi x pi. They're the same, right? So it doesn't matter which one you do. You're going to get the same result. I mean, provided you don't make a mistake, of course. But they're going to give you the same result if done correctly. It's just a different perspective. So let's clean this up a bit then. Either way, we can clean them up from here. You don't need a lot of cleanup on this. The 3 at the beginning is still 3. We have our 5. And we have a 2. And we have a pi squared. And we have the x. So all those can be moved to the front. So the 5 and the 2 can become a 10. There's a pi squared and an x. And then we have the sine of pi squared x squared. Or you could still leave it written as pi x quantity squared. That would be fine too. Okay, I think I have time for one more. This one's real quick, and then we'll finish up our last question next time with additional gateway review, okay? So this one right here asks us to go a little bit further, but it lets at least look at what happens with derivative perspective. So it says evaluate the derivative of the function at the given point, and then it talks about using the graphing utility to verify. So looking at this one, it kind of doesn't even look like a chain rule. I'll tell you what. Now it's doing what it did at the beginning of class. All right, so if we rewrite this as 5 and then it's x cubed minus 2 to the negative 1, we can see how it would be rewritten in a form that looks more like a chain rule. We can take the derivative by pulling that negative 1 down with a 5, so that's negative 5. We rewrite the inside and decrease our power by 1. And then we would take the derivative of the inside, 3x squared. Everything that's written to the power negative 2 can go back into the denominator, like so. And then the pieces that remain here at the end and the beginning can be multiplied to give me negative 15x squared. Now, you could certainly have stopped right here for the gateway, right? This question, however, wants us to evaluate it at a specific point. And the point it says that it wants to evaluate it at is negative 2, negative 1/2. And the MO for our book is that it always gives us the ordered pair. Some books and resources don't do that. They just give you the x value, which is fine too. All we really need is the x value to do this question. So we're going to evaluate the x value at the point negative 2. And keep in mind, some carefulness with your parentheses. This is negative 2 quantity squared, so that will be positive. But in the denominator, when I have negative 2 cubed, I'll get a negative. Oh, that's a 2, so there, sorry. There we go. And so then as we multiply and so forth, clean this up, we end up getting negative 3/5, or negative 0.6 would be fine as well. So when we come back next time, remind me, and we will take a look at the graphing utility to verify our results, because it's a really cool feature that you'll want to see.